Right, so ladies and gentlemen, glad to have you guys here tonight. Our speaker is Jeff Kuhn, and I've known Jeff for, what, over 10 years now, haven't I?
Closer to 20, actually.
No, it just feels like 20.
Yeah.
So yes, but long before either of us were around here. And since then, Jeff has been appointed as Associate Director of the Institute for Astronomy, and he's the Director of the Haleakala Division. He received his degree, his bachelor's degree at community college, Kalamazoo Community College, and then went on to Princeton. So, and he's also kind of an old salt. You'll have to ask him about the yacht race he was in. But yes, the one-time yacht race. But anyway,
You know too much.
yes, I'll leave the rest of the skeletons in the closet. How about that? But he's going to discuss today a lot of the reasons why it's so important for us to understand this, to study and understand the sun. And so, if we could give a big hand to Jeff.
Welcome, guys, to the second of our monthly talks. We're hoping we can keep this going for a while anyway, maybe not at a monthly pace, but something close to that. Okay, I'll try to speak up. Sorry. If I fade away, yell, and I'll try to bring up the volume again. So the subject tonight is what really is the connection between the sun and the earth. And I can't talk about the connection between the sun and the earth without talking about the earth. And the earth itself has a lot of complexity to it, and a lot of that complexity is wrapped up in the subject of global climate change. So we're going to talk a little bit about that, and we're going to start with this slide. It's one of my favorites. It's actually an old slide prepared by NASA years ago. You can see the last date on it is 1960. And I want to use it as a warm-up to get you used to seeing graphs, because I'm going to throw a lot of graphs at you. Apologies for that. There are even going to be some numbers and equations which you're free to ignore. They won't be on the test, but the graphs will be. This is a graph that shows, so remember how a graph works. So this goes back to 1880 up to 1960. And it shows two things. It shows what sunspots are doing, and we'll talk about what sunspots are. That's this solid line right here. And then it shows, for each one of these panels, what the rainfall is doing. Right around London, and right around Reykjavik, and right around Faroe, Alaska. And it has been used in the past to argue that the sun is almost certainly affecting our climate. You believe that?
Sure.
So this sunspot is basically the number of dark spots on the sun. We'll see some more of that real quick. And this graph right here is how much the rainfall has deviated. And the funny thing about this graph is, so if you pick Barrow, you find out that when there are more sunspots, there's more rain, going back a ways. If you pick Reykjavik, when there's more sunspots, there's less rain. And if you pick someplace near London, if you have more sunspots, there's more rain until about 1910, and then there isn't. So one of the issues that we have to face when we look at data graphs like this is, do we conclude from this that sunspots control the weather? Let me show you another graph.
Not on that one graph.
Not on that one graph. I like that answer. Here I've taken sunspots from a 30-year period a little bit later, from like 1960 to 1990. That's the sunspot number. And here's another plot. What do you think?
Dismal time in 1985.
Yeah, but do you think that the number of Republicans in the Senate is controlled by the sunspot number?
There's a correlation, but it's not necessarily causal.
More sunspots and more Republicans?
Yeah, right.
Does it mean Democrats are in the dark?
I'm not going there. Let's not go there.
That was pretty good.
My point, of course, is that when you see a graph, you have to take it with a grain of salt. There's statistics, and then there are damn statistics. And the point in all of these plots of weather and climate is that if you don't understand or cannot describe a causal mechanism, then what you're talking about could be nonsense. because in particular, when you go back to that plot of the weather, there are infinitely many places on the globe that I could take a weather pattern. And there could be a million different places where the weather is measured where there's absolutely no correlation. And by chance, you see curves that go up and down like those. So one of the lessons to come out of what I want to say tonight is that science is about finding cause and effect, not necessarily about finding correlations. And so we have to be skeptical and careful about that. And here's an example of that. And in fact, if you don't select the data and look a little bit later, here's from 1980 to 2006, I think is where I have data. Here's the number of Republicans, and here's the number of sunspots. And in this case, when there are fewer sunspots, there's more Republicans, and in fact, it breaks down here. So there isn't. I've given this talk before, and somebody said, well, how does that work? It doesn't. Okay, so what I want to do is I want to set the context for talking about changes in the sun and changes in the Earth. And we'll do that by talking about our timeline, our astronomical timeline. Okay, so for us, the universe started something like 15 billion years ago. Okay? And the solar system formed something like 5 billion years ago. Next big event for us. The next big event for us is that the Earth forms at about 3.8 billion years ago. And there's no life going on at this point, right? There's nothing that we can resemble to. We don't have complex life, so there's some algae going on here somewhere, some oceans. But complex life doesn't happen until the last 500 million years. And so let's expand that last 500 million years into another timeline. So trilobites and complex life happened about 570 million years ago, the paleontologists tell us. And the next event that's notable are the dinosaurs, right around 245 million years ago. Okay, and then sort of the next big event is the age of the mammals, which is 65 million years ago. Still no humanity on the planet. Right? And then finally, in the width of this line, which is on top of this line, which is expanded from here, we get our hominid ancestors about 3,000 years ago, or 3 million years ago, is where we can roughly trace something like Homo sapiens. And Homo sapiens is only about, K here means kiloyears, so it's 120,000 years ago. But then modern civilization is the width of this line, inside the width of this line, inside the width of that line, and that's the last 10,000 years. Okay, so modern civilization, in terms of the climate history or even the history of life as we know it, is just a blink. We're just a blip. 10,000 years of modern civilization is in fact a tiny fraction of the period of time in which two-legged creatures walked on the earth, our ancestors. And you might ask, and climate change maybe gives us a hint of an answer, why it is that it took so long for modern civilization to develop, given how long humanity in one form or another was on the planet. I wanted to point out to you that actually the coming and going of life is a very dynamic process. This is a plot that shows the percent extinctions in the biological families as a function of time. And so this is the green part of that curve, the last 500 million years before the present. And there are some blips in here that you might recognize. Anyway, this was about 65 million years ago. You know what this blip is?
End of the dinosaurs.
That's the end of the dinosaurs that we think was due to some sort of a bolide, some sort of a big object that struck near the Yucatan Peninsula, filled the Earth's atmosphere with debris which changed the climate. There was another blip back here, and another blip back here, which is even larger, which we don't completely understand. But there are blips going on all the time. Species are coming and going. That's good for us. May not be good for us in the future, but in fact that's what evolution is all about. Right? And so the total number of families has changed like that. So the message in climate change, just like the message in biology, is that the world is always changing. Constancy is not something that we are entitled to or we should ever expect. And I think that will come out of looking at some of these graphs I'm going to talk to you about. Okay, so climate records fall into sort of three categories. So remember that timeline. Modern civilization is the last 10,000 years. Hominid life forms are sort of the last 3 million years. But any climate record which goes back more than 1 million years is long-term, and it's probably not any good. We don't have very good climate records that go back earlier than about 1 million years. We have decent climate records that are in this range of less than 1 million years, and they're based on things like ice cores and sedimentation records in lake beds that have fossilized over time. I'll talk about some of those. But those climate records are reasonable approximations to things like rainfall or sea level or average temperature. Some of those things can be encoded in the ice or in the sedimentation. Then there are historical records, and in principle, we have historical records over a period of time where we have good word of mouth or where we have a written record. And we do have historical records for the sun and for some climate records that go back a couple thousand years. A good record of climate is in tree rings. There is a living sequence of the Joshua pine tree in California that goes back over 1,000 years. And that's a template that can be used for measuring and dating, but also it tells us about climate. Satellite observations go back only about 25 or 30 years. Glacial records go back only so far as the depth of the glacier. And the glaciers that we have access to in the South Pole or the North Pole are a couple of kilometers deep. And that turns out to be somewhat less than 1 million years. Okay, so this is the sort of the broad picture of where we learn about the Earth's climate. Now, the basic solar connection that we want to know about looks like this, right? So we got the sun, right? And the sun produces energy which comes over to the Earth. Now, only a certain fraction of that sun's energy makes it into the Earth, and that fraction that makes it in is related to something we call the albedo. Albedo is a number we're going to talk about. So the albedo is the reflectivity of the Earth. So a lot of that energy is reflected out. So the total amount of energy, and ignore the equation, just listen to the words if that helps, is just the total energy that the sun puts out. That's this number L. And it's modulated by how much is reflected away, and that's that number A. So L and A are things we want to know about if you're a physicist. But the temperature of the Earth depends not only on how much energy is absorbed by the Earth, but it depends critically on something else. Does anybody know? If you live out in the cold winter climates, it gets rid of energy. It has to get rid of energy, right? You don't count, Joe. It's how much energy the Earth radiates, right? You put insulation on your house, and you don't have to burn as much oil. You don't have to put as much energy into the house to have the same temperature, right? And so the Earth is also radiating out. Anything that has a temperature radiates. And so when the amount of energy that comes in equals the amount of energy that goes out, then everything is even, and nothing changes. And so the temperature of the Earth adjusts to the point where the amount of energy that it radiates out is equal to the amount of energy that it absorbs. That balance is called equilibrium. And as something gets hotter, it's able to radiate more. So if we get more energy, the temperature is going to rise in order to get rid of that energy. Okay? So this balance between how much energy goes out, and that depends on the temperature, depends on the fourth power of the temperature. It also depends on something that we call the emissivity of the Earth, how easy it is for that energy to pass out of the Earth into space. So the amount of energy that the Earth is able to get rid of depends on the temperature of the Earth and the amount of and its efficiency, how easily the energy can escape. When these two things are equal, we can figure out what the temperature of the Earth is. And we can calculate that. We know how bright the sun is. It depends, of course. Okay, so the temperature of the Earth depends on how bright the sun is. It depends on that albedo, how much energy is reflected away. It depends on the efficiency for how well the Earth is able to radiate away the energy. And then it also has to depend on the distance, right, between the sun and the Earth. Because the energy from the sun is being diluted as it travels outwards. And so the amount of energy that the Earth actually intercepts gets less as we get further away from the sun, right? If you move away from a fire or a light bulb, the light bulb gets faint. Okay, so if we take everything that we think we know about the Earth, the number works out to about 288 degrees Kelvin for the temperature of the Earth. Kelvin is a funny way of measuring temperature. 0 degrees Kelvin is absolute zero. So this is, in Celsius, is about 215, is about 15 degrees Celsius. So the average temperature of the Earth, according to physics principles, is 15 degrees Celsius. That's a pretty crude estimate, right? Because the average temperature of the Earth varies from the pole to the equator, from night to day. So this is just an approximation. But this is the beginning of understanding the connection between the sun and the Earth. So if we were to increase the luminosity of the sun, what's the temperature of the Earth going to do? Go up. If we're going to increase the albedo of the Earth, what would the temperature do?
Go up.
It would go down. Albedo is how much energy is reflected away. If we were to increase the emissivity, what happens right here? If we make that bigger, it would go down. If we were to increase the distance, the temperature would also go down. Okay, so with this rough equation here, we can figure out how all of these effects change the temperature of the Earth. And the temperature is a good measure of climate for us. So I want to use that as sort of my template for describing all these other effects in climate change. Okay, so what should we be worried about if we're going to change the temperature of the Earth? Well, changing D, right? The distance of the Earth to the sun, if it changes, is going to change the climate from that equation that we saw. And that can change over long periods of time. The orbit of the Earth doesn't have an average. For a single orbit, the distance from the Earth to the sun changes by a few percent. But over longer periods of time, those changes could be systematic and important. L, the brightness of the sun, can change. That we're going to talk about a lot, because that's something that we as people that study the sun, really care about. The albedo could change. The albedo depends on lots of things. One of the big things it depends on is the cloud cover. If you increase the cloud cover, clouds can reflect more of the energy. And so if you don't understand how the clouds are changing, you can't say how much energy the Earth is actually absorbing. The reflectivity, as the area covered by land versus water changes, that changes the albedo. Because the land reflects heat differently than the water. Land reflects more heat than water, so having more water will decrease the albedo. The emissivity has to do with how much the atmosphere blocks the radiation from escaping, and that's when we think about greenhouse gases. So if we have greenhouse gases, those greenhouse gases will tend to prevent the radiation from being emitted out into space. And so the emissivity changes in response to the greenhouse effect. So the greenhouse effect, let me remind you, is when light comes into the greenhouse at the wavelength of light, which is visible light, that's where most of the energy comes in. It heats things up. Inside the greenhouse, they have a temperature like our temperature in this room. And when we radiate, and our radiation is blocked by the glass. The glass doesn't let the radiation of the plants in the interior of the greenhouse out into the atmosphere. And that's how the atmosphere works around the Earth at some level. It prevents the escape of radiation, but allows the input of radiation through the clear glass of the atmosphere. Okay. Talk a little bit about that. So these are all possible causes for climate change, and we have to understand all of these before we can talk about what causes the climate or the temperature of the Earth to change. So this is a complicated story, and no one has the answer to all of it, and I'm going to try and give you some pieces of it. And I'm not an expert on all things, especially related to the Earth's climate system, but maybe we can blunder through some of this and, through a deductive process, talk about where the important parts of the problem are. Okay, so long time scales. We said we didn't have a very good climate record, and it's true. And one of the reasons is that we know that this is a great puzzle. The sun is 30% brighter, more luminous now than it was when the Earth was formed. It seems odd, but it's a fact that what happens as a star burns, it converts hydrogen into helium. So it takes 4 hydrogens and converts them into 1 helium atom. That's fusion, that's the fusion process. So the total number of atoms in the sun is decreasing. They're going from 4 to 1. Because the total number of particles is going down, the temperature actually has to go up. We've studied a little chemistry. And it's an ideal gas law, and that means the sun actually has to get hotter as it ages. So the sun ages and we're 30% brighter than we are now. That's a mystery to us. Because if we were to change, remember that first calculation we did, we said that for the solar luminosity that we now have, the Earth should have a temperature of, what do we say, 288 degrees Kelvin or 15 degrees Celsius. If the Earth were 30%, if the sun were 30% fainter, what would happen to the temperature of the Earth? It would go down. Do you know how much it would go down?
Quite a bit.
Well, it would go down, so that equation was a fourth root. Fourth power, so it's 30%, it's sort of a small number, so roughly 1/4 of 30% is how much the temperature of the Earth would go down, so it's about 7 or 8%. If you took 7 or 8% away from 288 degrees Kelvin, what are you going to get? You're going to get something which is about 260 degrees Kelvin. But you know what the freezing point of water is? It's 273 Kelvin.
So below freezing everywhere.
So one of, and this is called the faint young sun paradox, and we don't have an answer to this problem. There must have been a time where, unless something else changed, the Earth was completely frozen.
There's a heat of formation.
Well, heat of formation I don't think does it. The likely answer is carbon dioxide, but the problem, once the Earth is frozen, it actually will never warm up. Because when it's frozen, it now reflects most of the light, because it's all ice. And ice is very reflective. So if the Earth were ever frozen, it would never warm up enough. Even though the solar luminosity went back up to that higher value, it's not enough to thaw out the ice, and that reflectivity doesn't take us back to the original brightness that we started with when the Earth wasn't frozen.
Well, there might be some liquid pools from tectonic features and so on, and that
But he
could
means
cause
that-
carbon dioxide to come up. And
Could be, could be.
we
People
also have
speculate.
radiation that's going on, and this process that could change with time. I mean, it's things to think about.
Those are good things to think about. And one of the, and you mentioned one of them, which I think is the leading theory for what the solution is, was that there was 1,000 times more carbon dioxide, greenhouse gas, in the Earth's atmosphere back in the old days, billions of years ago, than there is now. And so the emissivity was reduced, so the Earth was much better insulated, so it could heat up to a higher temperature in that case. And that's one of the theories. The other is that maybe we don't understand the sun well enough, and that there's something else that went on that didn't allow this luminosity change.
Is the luminosity getting straight line?
It's mostly a straight line. It's pretty linear. So the other problem with talking about climate change over tens or millions of years is that the Earth looks a lot different, right? You've seen pictures of the Earth if you go back 260 million years ago. This is all the continents are all wrapped up together.
Maui?
Maui is just a twinkle in somebody's eye. Pangea is the name of this supercontinent, and so the ocean circulation is completely different. Climate is not describable if you go back far enough so that the motion of the continents has to be accounted for. So we don't really have much to say about these long time scales. That's the point of my message here. There's too much uncertainty. On slightly shorter time scales, some interesting things are going on. One is that the eccentricity of the Earth's orbit, which is the Earth's orbit is slightly egg-shaped. It's varying. It's changing in time. The other thing that you may know about is that the Earth's axis is tilted, and it's orbiting with a tilt which is actually spinning or precessing like a gyroscope.
I mean, the line about which it precesses is not normal to the plane of the orbit?
It is normal to the plane of the orbit. So this is the normal to the plane of the orbit, and so it's doing this.
Yeah.
And that takes some number like 20,000 years to go all the way around. This number, so the other thing that the Earth's orbit is doing is it's doing this. So the angle that it makes, it's wobbling up and down a little bit. So the Earth's spin axis goes up and down, and that takes about 41,000 years. And then the eccentricity takes about 100,000 years. So all of these cycles we can actually compute because they're due to the effects of mostly Jupiter in the solar system and how it perturbs the Earth. And what they do is they tell us that on average, the amount of energy that the Earth absorbs, so this is a scale here which goes thousands of years, here's 1 million years here, that the amount of energy the Earth absorbs is going up and down by, so this is 420 and this is 500, so it's going up and down by about 30%, 20%. So this is a change that should show up in our climate system because it's the total amount of energy that gets into the Earth. And Milankovitch in the late 1800s, early 1900s, was one of the first to argue, they call it the Milankovitch cycles, that there were long cycles, long periods in the climate history of the Earth. And guess what? We can see those long climate cycles if we go to ice core drillings. So here's a picture of one of these. So ice cores are about like this. You go down a couple of kilometers, you pull them out, you take them up into sections, then you take the ice core, and it's water mostly, right? And you go out and you measure the ratio of, there's a variety of oxygen that has 2 extra neutrons. It's called an isotope. It's called oxygen-18. Heavy water. Heavy water evaporates at a different rate than light water from the surface of the ocean. And so, if I could show that schematically, the ratio of heavy water to light water is a temperature. It's a thermometer. So if you can go into that ice core and measure how much heavy water there is compared to how much normal water with the oxygen-16, you can measure effectively the temperature of the ocean, or that body of water that produced the gas that's up in the atmosphere, that falls down into a bunch of layers in a glacier. Okay, so all you have to do to measure the temperature of the Earth is you take your ice core drilling, you count the number of rings or layers, so that's the date, you know, how many years back in time you've gone. Take a sample of that, go to a mass spectrometer, and measure the ratio of the oxygen-18s to 16s, and that gives you temperature. And the record is pretty interesting. Here's a record that shows that, so it's been converted to a temperature scale, and there's some uncertainty in that always. There's some interpretation that goes into it. So here's the present, and here's back 160,000 years. And here's the temperature, so modern civilization, so here's 20,000 years, so modern civilization is right up here. Okay? This is the normal appearance, and then there's another warm blip over here. This is a plot that shows what we know about ice ages. The Earth is mostly covered by ice most of the time. And it's only during these warm blips, here and here that we're in, where the ice goes away and the temperature warms, on average by, what's the scale here? That's minus 10 degrees Celsius. So if you change the temperature of the Earth by about 10 degrees on average, you go from an ice age to what's called an interglacial. And those interglacials happen something like roughly every 100,000 years. So what do you think causes the interglacials? What causes the warm periods? It's probably these orbital effects. It's the conspiracy, it's the rhythm of the eccentricity of the Earth's orbit and the tilt of its axis and the precession of its axis. It's that symphony of those effects that causes a change in the insolation and a change in the average temperature of the Earth that makes the ice ages. That's the theory. If you now go to the computer models of climate, you ought to be able to reproduce that, right? We know what the orbit is doing. We can throw the change in amount of energy into the computer models, and we ought to be able to get what we think measured by the ice cores. The answer is we don't. The models do not reproduce these long-term changes. They're incomplete. We know that must be the physics, but we can't in detail make things match up. Nevertheless, we're going to go on and we're going to say that the ice ages are caused by orbital effects. And it's pretty clear that they correspond to periods of time which are maybe 10, maybe 20, maybe sometimes 30,000 years long, when the temperature is warm enough for us to feel comfortable. Yes, sir?
You say that the computers did not verify the theory,
That's correct.
but they continue with the theory.
I'm going to have more to say about that. So the details of the theory, the details of what are called global climate models, we want to try and reproduce what the Earth's temperature is doing. And they do not succeed in reproducing this fact. So you want to calibrate things. You want to prove that somehow the models are right? By taking something you know must be true, the changes in amount of energy due to the orbital changes, those models are accurate. We know how to do the orbit of Jupiter way back in time, and we know how it affects the patterns of the Earth's orbit. We know that must be right. And we do believe there's nothing wrong with this real measurement of the temperature of the Earth. So we have what the Earth is doing, we have what the inputs are doing. A test of any computer model of climate is that it should be able to reproduce that. That hasn't happened yet. I was going to show you in more detail the record. So this now goes down, and this represents the temperature derived from the oxygen 18 to oxygen 16. And so there are actually two records here. So this goes down to a depth of, let's see, so this is measured in meters. Okay, so we've gone down 1,500 meters to here, and this is 1,500 to 3 kilometers basically over here. So you have to put this on top of that. Now, the other scale here is the depth in time. So in the first 1,500 meters, we go down 10,000 years. In the next 1,500 meters, we go down 250,000 years. Why is it that the first half of the ice core corresponds to 10,000 years, whereas the last corresponds to 250,000 years?
Compression.
Compression, exactly. So what's going on here is in the first half of your ice core, you can measure the time by actually counting strata. In the deeper parts, the strata get all compressed together. And you have to have a model for how ice compresses to know what the time is that corresponds to that depth. Okay. So things get a little squeezed up in here. But nevertheless, what's striking about, and so here's our temperature scale, okay? A 15-degree temperature difference corresponds to the length of that arrow. All right? What's different about the last 10,000 years compared to the previous?
They've barely been changing.
There is this dramatic stability in the temperature of our climate in the last 10,000 years, which is never reproduced in the previous 250,000 years.
And what was different?
When did civilization appear?
It came.
Within the last 10,000 years. So the previous interglacial is right down here. So this is this warm period over here. This is all cold to the left. And then when it's cold, it's fluctuating a lot. And here's the previous interglacial. So this is roughly the 10,000 year span corresponding to this. It's just been compressed. Notice also the previous warm period. Look at how it fluctuates in that warm period. So the other thing that's magic about this, so you can't see those fluctuations in this curve because that's been smoothed. So if you want to see the fineness of the temperature change with time, you have to look over in this curve. But this bump here corresponds to this bump. And the really fascinating fact is that if you go to the last interglacial, temperature fluctuations are huge compared to the ones here. Why? I don't know. Nobody knows. A lot of the fluctuations that we see can be attributed to volcanism. Some of the events in this record, you can actually see a stain where volcanic activity dropped material into the snow that appeared in the ice core record. Many of these events have no explanation. Yet they describe a temperature change which could be 5 or 10 degrees over 100 years, 100 years sounds like a long time, but 5 or 10 degrees is half of the total range. 5 degrees is half of the total range in going from an ice age to the current interglacial period. So I find this a little scary, that civilization may be a consequence of some sort of accident of the climate system over the last 10,000 years. Okay, so I've made this point already. We do not understand the interglacials. They're not reproduced by our models. The other possibility for climate change we talked about was the sun. So let's talk about solar variability and what the sun may do. So I wanted to remind you that actually the sun is not constant. This is that Halloween event about 4 years ago, almost 4 years ago. You remember that? So these are images taken in white light of the sun, and that's an enormous sunspot which grew faster than any sunspot we've seen in record. And in fact, there was a solar storm that I'll show you an image of in a minute, which was larger than has ever been recorded. So the sun can do some pretty dramatic things. And within our lifetime, in fact within the last 3 years, we've seen the biggest event that we've measured since we've had satellites in space. Now we think there was one event larger than this back in 1863. How could we possibly know what the sun was doing like sunspots in 1863?
Was that mini ice age?
1863? No, that was a little bit further back. In 1863, we were laying out telegraph lines across the U.S.
Oh.
Telegraphs had just been commissioned.
Oh,
crazy.
detected the...
Fires were started. The geomagnetic disturbance associated with a flare event in 1863 was so intense that it caused telegraph offices to burst into flames.
Induced voltages in the long
Induced
lines.
voltages in the long lines of the telegraphs.
Until they figured out how to put fuses and ground and
I put fuses and ground and everything else. But there was a visible record of a storm and sunspot development by Carrington at the time. It was a British astronomer.
Yeah, they could look at the sun in that day, in those days.
They did, but they didn't know that there was a geomagnetic connection.
But they could see lots of sunspots. I presume it was
Were there auroral events and things like that that were recorded?
Aurora we're seeing all the way down into Hawaii, as I understand it.
Really?
So it was the biggest solar storm event that has ever been recorded.
Sneeze.
What's a royal event?
Auroral.
For those that live in Hawaii and have never been to the north, I grew up in Michigan, which is a good place for Aurora. The sky lights up with a curtain of light, and after a solar storm, maybe I have a picture. Let me answer that question in just 1 second when I show you some other images. This is what a sunspot looks like in more detail. A sunspot is really not a very friendly thing. It's
What's the scale on that sunspot?
so the Earth is about this big. Okay, so it's huge. And a sunspot is really just a defect on the surface of the sun. So these are those objects that you saw floating around. At the highest resolution, this is what we see. We see an outer region called a penumbra, and then we see a dark inner region.
It looks like gases falling into a hole.
It doesn't, but if you have a spectrograph and you actually measure the Doppler motion of the gas, you find out the gas is actually moving outwards. So this is an illusion of the pattern. The pattern that's there. The scale here, there's obviously lots going on. A lot of what we want to try to understand is why sunspots do what they do, why they cause the storms they do. And it's clear that in order to understand that, we have to be able to see more detail. But I wanted to show you what one of these looks like in detail that we know. The sunspot is really just like a great big bar magnet. So it's like you have a bar magnet, and sunspots usually occur in pairs. And so this is a sunspot at the edge of the sun, and you can see the magnetic field lines just as they were drawn when you learned about magnetic fields in school. If you had iron filings on a piece of paper, the iron filings would line up like that. And so there's field coming out with the South Pole here and field going in with the North Pole here around these sunspot pairs. And that's what we think is going on with the sunspot.
And what about the physics of that?
Well, we'd like to know about it. Here's a picture which is a magnetogram. So we can measure magnetic fields. The magnetic field on the Earth, anybody know how strong it is? It's the thing that makes your compass needle turn.
Half a Gauss.
Half a Gauss. Perfect number. half a Gauss is just the number that we associate with how we measure fields, magnetic fields. The magnetic fields in sunspots, and they occur in pairs, so this is field coming out and the blue is field going in. That field is 3,000 Gauss. So it's a pretty strong field. It's not the strongest field we can make in the laboratory, but it's much stronger than anything we worry about on Earth. And
It's due to convection of charged particles, I presume, is what induces that field, as part of it.
but detailed models of how you make that work don't
It's a mess.
work out. Yeah, it's a mess. So the sun is rotating, so now we're going to peel it off so you can see the sun.
Nice thing,
Now, I didn't make this movie. Now we're going to watch, this is the year down here. And so notice that as the solar cycle progresses, we go to periods where there's no sunspots at all, hardly any. That's around 1985. And then we get all kinds of sunspots around 1990. And very few again in 1995. And then lots of them again right around 2000.
22 years,
Okay? So every 11 years, the sun has this rhythm where there are lots of these magnetic fields and lots of sunspots. And then in between, there are very few sunspots. And that's called the solar cycle. So the sun is intrinsically a variable thing. It's a star that's changing, and its changes are things that we'd like to understand. Okay, so what did we say? We said in when were there lots of sunspots? It was right around,
No, you said
It's right-
1863.
well, there were few around 85, right? And right around 1990, there were lots of sunspots. Okay, so this is a plot. This is a plot that shows the year down here, and it shows, so from a satellite above the Earth, we can measure how bright the sun is. We can just measure the amount of energy. Of course, it's changing its distance, so we have to correct for the orbit of the Earth, but we can measure how bright the sun is. And this satellite, a series of satellites, has been looking at the sun since back in the late 70s. And the interesting thing about all of these, so there are a bunch of them, they don't live for that long, so we have to compare one to the other. And the fact that they measure differences from the same satellite says that, well, so there's a calibration thing. But the record I want you to look at is this record of brightness. And this is an interesting number. That's the number of watts per square meter that hits the Earth above the atmosphere. Okay? And
Not a big variation.
it's not a big variation, but it's pretty clear that it is a variation. And what's the rhythm of that? So there's a peak in 1980, there's a peak in 1990, so it's 11 years. So the brightness of the sun is changing in synchrony with the sunspots.
And the luminosity due to the sunspot, umbra isn't enough to make up for that, I take it.
Well, what do you think? So
But how about the area outside the umbra? Does that get brighter?
those are all good questions. Those are great questions. And notice that the amount by which they get brighter aren't going to be great numbers. Let's first ask the question, is it brighter when there are more sunspots or fewer sunspots? What do you think the answer should be?
Brighter.
Brighter with more sunspots? But they're dark things.
No, but that's such a small,
That's not the way to
it's
get
such a
it.
small part of the sun.
Well, of course, I'm trying to pull you into something.
I'm not going for it.
You're not going for it. Well, you're right. If we go back and look at that movie, we'll find out that there were more sunspots in 1990 and fewer sunspots in 1985. So the sun is brighter when there are more of these dark things on it. All right? So the other thing you can notice is the dark things really do make the sun darker. And so these excursions you see here, these excursions in the brightness on short times, these happen short, that's when a sunspot appears and rotates across the disk, and it makes it darker. So an individual sunspot makes it darker.
I would think when there's a lot of solar activity, there's more mixing going on, and the reaction rate, the fusion reaction
But
rate.
that's
must
occurring
go
way
up.
deep in the sun, though.
The stuff that gets out.
These are all good
to the
ideas.
surface.
You guys come do some astrophysics. Your answer is correct. The fusion that takes place when a fusion reaction takes place in the core of the sun. You know how long it takes for that energy to get out to the
Thousands of
outside?
years.
Hundreds of years.
It takes a million years.
Really?
It takes a million years. So anything that we see that happens on an 11 or 22-year time scale.
Does it get trapped in the long magnetic path?
No, it takes the random walk. It takes that energy that long to bounce around and get out.
Wow.
Because it's opaque.
And
That's a
see,
big
that's
distance.
a different cycle with a million-year relaxation time. This stuff is, due to
Just for it to get
sunspots.
out.
Well, it's due to something, and the mystery here is that when we got more dark spots on average, the sun is brighter. And it's brighter by an amount which is just 1/10%. Okay?
Huh.
And we don't have an answer
Turbulent
to it.
mixing in the photosphere.
That's what
My vote.
That's no reaction.
We'll talk about
That's not a reaction. That's not-
Solar radiance is directly measured to vary by 1/10%. The sun's brightness changes by only 1/10%. Here's the temperature of the Earth. So here I've plotted again another graph from 1978 to 2000. This is the brightness of the sun. Okay?
Uh-huh.
This is the temperature record from satellite observations of the Earth. Now, it's been worked on a little bit. We've removed events like, we will remove, this is El Chichon. This turns out that, it caused a brightening right here. And this bump right here was Pinatubo. Remember that?
Does
So-
St. Helens big, it doesn't show up, it's too small.
Which one?
I think St. Helens didn't show up,
No.
it's too tiny.
That's not on there. But look, there is a hint of that cycle in the Earth's temperature record, along with other things. So the solar signal does appear in the temperature record of the Earth, and we can measure how much the sun's brightness change with this 11-year cycle changes the temperature of the Earth. And what we measure is that 1 watt per meter squared difference in the brightness of the sun should produce 1/10 of a degree Celsius difference in the temperature of the Earth. Now that's not much, right? Remember that the scale to go from an ice age to a non-ice age is 10 degrees.
Yeah.
So this is 100 times less than that, and it's 1 watt per meter squared change per. Well, here's another problem. If you go to the global climate modelers and you ask them, okay, change the amount of solar energy by 1 watt per square meter on your model, how much does the temperature of the Earth change when you build that into your circulation model and the ocean currents and every piece of physics that you know about? The answer is you get a number that's half as large.
Well, one can imagine, though, there's a lot of energy from the solar wind that's being dumped into
That's not so much. You can
our
calculate
atmosphere
that.
as well.
We can calculate that. But I'll talk about the stratosphere in just a second, because that is significant. Okay, so the sun's variation is more than just total energy. We need to talk about some details of it. And we're going to get to your question. We're going to talk about the spectrum of the sun. This is a nice picture. If you had color film and a prism, and you could spread out the light of the sun from the deep red, and then you spread it out and then you stack it up. So I can't, my spectrum is too long, so this has been stacked up so you can see it. So from the deep blue to the red, this is what the spectrum looks like. Notice there's some dark spots on this. You know what the dark spots are? They're called Fraunhofer lines, and they're due to the atoms in the atmosphere of the sun that are absorbing that energy. So this line right here, it's called H alpha, and that's due to hydrogen in the atmosphere of the sun. These two lines right here, they're yellow. That's sodium, right? Those are sodium lines. That's the same lines that produce energy in a sodium vapor lamp. That's why sodium vapor lamps are yellow, because the sodium makes this yellow light.
Is our atmosphere dense enough so where oxygen and nitrogen also show up as absorption?
They would, they do. At the resolution of this, they're in this spectrum, but they're very narrow lines compared to the solar lines. And they're part of the...
Is that due to Doppler broadening?
The temperature of the Earth is much less than the temperature of the gas of the sun, so the broadening is more for the sun. Okay, this is one way of looking at the energy that comes to us from the sun. Another way is in this graph. So if we graph it, all right, so this represents color along this axis, okay? So blue is to the right, blue is to the left, and red is to the right. And this curve right here tells us how much energy the sun is producing, and every one of these marks means another factor of 10. So if you come over to this peak right here, so this is visible light, happens with this wavelength. If you go to the red, this is all infrared light. If you go to the blue, this is ultraviolet, this is extreme ultraviolet, this is X-ray.
Is that mostly just black body radiation on
Look
the
at the
right?
departs from black body in a high wave.
This is black body, this is not black body.
Yeah.
That's something else. But look at where most of the energy is. most of the energy is in the visible.
Yeah.
Yeah.
It's no accident that our eyes evolved to be able to see where most of the energy is, right? Our eyes work in the visible, where the peak, where most of the sun's energy comes out. Okay? But there is energy which is about it's about 1,000 times less than the energy that comes out in the visible in the ultraviolet and in the X-ray. So the sun's producing X-rays, it's producing ultraviolet energy, but it's much less than the total amount of energy in the visible and often the infrared. Okay, the green line is also important here, because the green line, if you read off on this scale, tells us how much that energy varies in 11 years in terms of fractional amount. So remember we said that the total energy of the sun is only changing by 0.1%, right? So in fact, most of the energy is coming out in the visible, and here's 0.1%, 0.001. So it's a fractional, so 0.001 means 0.1%. So most of the fractional variation of the energy of the sun is pretty constant, only changing by a few tenths of a percent on this scale. But as you go to shorter and shorter wavelengths, the sun gets much more variable. Here's 100% right here. So that by the time you get into the ultraviolet and the X-ray, the sun, if you could see the sun in X-rays, it would be changing its brightness all the time by a huge amount.
How about the corona versus the photosphere? Have people looked at that contribution?
The corona is 1,000,000 times fainter than the photosphere on average,
But the
except until
fluctuation-
you go into the X-rays.
Yeah, that's what I'm looking at, and yes. I've just noticed when you look at a total solar eclipse, the unearthly light, because there's so much in the ultraviolet part you can't see, but you can certainly sense something's different about the quality of the light from the corona.
Well, it's almost a sort of a mystical feeling.
It is.
I've been to a bunch of eclipses,
How
and
many
strange
minutes?
things happen. and during a total solar eclipse, other things happen. But the corona is very important for the very blue light, the X-rays and the UV. It has very little contribution out here because it's just too faint. Okay, so the variability of the sun depends on the color, and the sun is mostly constant out in the visible and the infrared. Am I getting too technical?
Not really.
Not yet.
Okay. You guys, all right, I will try to speed up here just a little bit. You know what the Earth's atmosphere looks like? What happens as you go up in height?
Less.
It gets colder and it gets less, and that all happens down here. Do you know what happens when you get to about 10 kilometers up? It warms up. It starts to warm up. It starts to get hotter. And that marks what we call the tropopause in the stratosphere. And in the stratosphere, so this is a line that shows the temperature decreasing and then starting to increase up to something called the stratopause. Do you know why the temperature is rising once you get up to about 10 kilometers? Anybody know?
Says UV absorption on your...
Oh, you're reading my... It's because we're making ozone. We are absorbing energy, ultraviolet radiation in that regime. The UV radiation penetrates to that height in the atmosphere, and it's absorbed. All of this temperature rise is due to the absorption of the sun's extreme ultraviolet radiation. So when people worry about the ozone hole, they worry about us losing that ozone and allowing the ultraviolet radiation to penetrate deeper. So there is a significant amount of energy, still fractions of a percent of the total energy, but energy which is being absorbed in the atmosphere up high. And it has to vary a lot, because what did we just say about how much the sun is varying?
It's varying out in the UV.
The sun varies enormously. It can vary by 100% when we go to the XUV. So the sun changes its brightness by 100%, and that means that the stratosphere has to be changing. Now the climate people don't know how to make changes here propagate down into the troposphere. But we do see those changes in terms of the effect on the jet stream, which is right up here at this boundary, and in terms of something called the biennial oscillation of the stratospheric winds. So there's another connection between the sun and the Earth, where changes in the sun are important to what happens in the Earth. And that happens up in our stratosphere. I wanted to point out that the sun is extremely variable, and this was a good way of showing it. For a long time, we've had satellites that orbit the Earth and monitor the X-rays from the sun. So not only on the solar cycle, but this was during that, remember we saw that big sunspot grow about 3 years ago around Halloween. The NOAA monitors, right about the same time, were measuring the amount of X-rays above the Earth's atmosphere. And so this curve right here is kind of interesting. So again, each one of these lines means a factor of 10 more. In the span of just a few seconds over here, the energy in X-rays increased by more than 1,000 times. If you had been outside a spacecraft at that time, it would have been a lethal dose of X-ray radiation. The Earth's atmosphere responded by swelling out due to that. Satellite, the effect on satellite drag was immeasurable because of what the sun did to the outer atmosphere as it absorbed these X-rays. So the sun is connected to us in our outer atmosphere, not just on solar cycle timescales, but on very short timescales by these bursts of energy that we call, I think the next picture shows that. This is a side view of the sun, and the sun is here, and what you're seeing is a bunch of hot gas and particles being expelled into space. That's called a coronal mass ejection, and it's due to one of those sunspot regions hiccuping, releasing a lot of energy and spitting it out into space. And luckily these storms went off to the side, not towards the Earth.
Was that magnetic bubble that burst, that where you can see the mass coming back in? Looks like it
No, that
comes
was a
back.
comet. That was a comet which actually died. It struck the sun. It didn't come out the other side.
No kidding.
Yeah, there are a lot of them that were discovered by this spacecraft. So the other thing that happens that's important for us is that this is a simulation that shows another connection between the Earth and the sun.
And these are big, enormous computers to do that plotting you're getting them to do, I take it.
Well, this is the wind from the sun. This is the magnetic field of the Earth that's protecting us.
These
you're
are- this
seeing-
is- This is real data then.
It's a simulated data. We don't have a
So it's
satellite.
big
that can see
computers,
this.
yeah,
Yes,
okay.
that's what it is. So this is what we call space weather. There's not just weather on the Earth, but there's weather in space. And it's the interaction of the sun with the Earth, with these energetic particle events. And that's an important connection. We lost satellites during this big storm. 2 satellites were destroyed. Planes were rerouted. I don't know if you noticed, newspaper carried stories of the polar transits, the polar trajectories of planes from Hawaii were diverted because there was no communication and because the radiation associated with the commercial flight at these elevations was too high. So there's another connection here, which is through these short time events. And schematically, we could draw a picture that looks like that. So there's the energy of the Earth, the energy of the sun that intersects the Earth and heats the Earth. And then there's this variability at very short wavelengths and with particles that interacts with the outer environment of the Earth. And all of these things are measurable. Okay, so I wanted to summarize all of these. In total energy, the sun is connected to Earth by spectral variability. The magnetic fields that I showed in that last picture connect the sun to the Earth. And by particles, the solar wind that we talked about. All of these are connections and they're measurable. All right, now let me get to the last part of this talk, which is to ask 2 questions. Do we understand the short-term historical climate changes? What are they? This is a good plot. This is a plot that was constructed from historical records and modern records of measurements of the sea surface temperature. Turns out the British Empire, which extended over much of the globe in their ships, went out and they measured the water temperature with canvas buckets as they traveled the oceans. And those records go back to 1860. And notice what the record shows. That the temperature of the Earth has gone up from an average, so this is an average that is based on this average right here around the late 1800s. So compared to the late 1800s, the temperature of the Earth has gone up by 0.6 degrees Celsius. How does that compare to the temperature changes we were talking about? Pretty small, right? The change that goes from the last interglacial changes were a factor of 10 larger.
Yeah. More.
2 things are notable here. One is there's a big rise in the temperature from the 1900 time to about 1940. Then there's a constant or even falling temperature between 1940 and 1970 roughly. And then there's a rising temperature between about 1970 and 2000. So if somebody shows you a temperature record and they only show you this part of it, ask to see the rest of the data. Remember the lesson from looking at all of the data, not just parts of the data.
Yeah.
This is a reconstruction. We don't have good temperature records that go back, but we have proxies based on radioisotopes and a range of other measurements. Some of this may be actually use tree rings, although I forgot.
What is the vertical scale here? That's
So this is
temperature
temperature now. This is temperature in Celsius. Here's the temperature rise that we were talking about, which is about 4/10 of a degree. This is somebody's prediction into the future. This is a proxy interpretation back 1,000 years.
That's man's, right?
Yes, this is the man curve. This curve has been used to argue that temperature changes only in recent times are large, and if you go backwards in time, temperature changes are small. Now, that's possibly true, but there's a difference between this temperature record, which is a real measurement, and this one, which is based on some kind of extrapolation.
Yeah.
The other thing to notice is the uncertainties in the extrapolation are represented by the gray region. So there's an enormous uncertainty in those extrapolations, which extends to the range of the temperature extrapolations into the future. Nevertheless, it's a measurement or it's an extrapolation, which might be correct, and may be saying that temperature fluctuations now are larger than they were in the last 1,000 years. Does carbon dioxide explain the temperature record? Okay.
Does in the ninth circuit as of yesterday.
Oh no. Oh no. I haven't heard about this. Well, you do know that the temperature is rising, and I just wanted to show you pictures that you've probably seen. This is a glacier in Switzerland from 1870, 1931, and 1994. And the glacier is here, and the glacier has clearly gotten smaller. The glacial record has been measured very carefully over many years, and is shown in this blue curve. So here's a blue curve that shows the glacial trend, glacial shortenings, and it's based on measuring some fiducial length for all the glaciers for which there's a historical record. But also plotted on this scale is our coal consumption, our oil consumption, and our gas consumption. And these curves are a good measure of what CO2 is doing, as I'll show you in a minute. Right, the CO2 production is well correlated with our burning of coal, oil, and gas.
But just because it's correlated, couldn't that be like the number of Republicans versus sunspots?
It could be, but it's actually worse than that, because you'll notice that there's virtually no consumption of coal until, and it's even flat here, and the real steady rise doesn't happen until about 1940, after World War II.
Yeah.
There's a much smaller consumption of these non-renewable energy sources before that. But look at this curve. It started rising 80 years earlier.
Yeah.
Not only that, the slope here, the rate at which we're burning coal or increasing to burn coal here, it's flat, and then it rises, and that's not reflected in these curves. So this trend right here was going to happen regardless of what happened with coal, gas, and oil.
Did anybody tell us that Al Gore?
Anybody tell Al Gore about this?
You remember the scene in The Inconvenient Truth where he pulls that jack stand creation and he dramatically shows how the temperature of the Earth is going to rise? Temperature of the Earth was going to rise regardless of what goes on
that was
here.
happening or not.
It's
Yeah,
not
okay.
caused by the CO2. Because that
Those
happens.
hydrocarbons.
You're saying you can take the fossil fuels out of it and no change?
Oh, I can't say that. I can't say that, but I can say that this rise in temperature
already
is
happening.
not due to the CO2. This may have contributed to the rise in temperature, but we certainly cannot say that this rise right here was caused by this consumption of fossil CO2
Yeah,
sources.
okay.
And let me go back and show you that other curve that was CO2.
You need convenient life, because now you got a Pulitzer Prize for it, I'll never figure it out.
So look at this right here.
Yeah, no, well.
So I wanted to show you the CO2. So this is CO2, which we can also measure in ice cores,
Yeah.
because we can sample the amount of CO2 directly by pulling out air bubbles.
Mm-hmm.
And the CO2 fluctuates in natural cycles by, so this goes from 280 parts per million down to 190 parts per million. So that's almost a 50% change in the CO2, which didn't have anything to do with fossil fuels because we weren't around 40,000 years ago,
Yeah.
and 100,000 years ago.
So something else is going on.
So the CO2 cycle, the CO2 fraction in the atmosphere is caused by lots of things. And this climate change that you see here, which is correlated with the warming, right, doesn't define the causal connection. This change in temperature wasn't caused by that CO2, was it?
No.
It was caused by the insulation change and the orbital effects. So when you look at a correlation and you say, oh, CO2 is going up, therefore the temperature is going up. CO2 makes the temperature go up. That's not logical.
It does, but
It's
how
not
much?
that's not a causal relation. It's not a causal relation. We can see it for two reasons. This temperature wasn't caused by CO2, it was caused by insulation.
Uh-huh.
And the change that we saw in those graphs had the temperature of the Earth rising before the CO2 production went up.
It's also not rising as exponentially fast as the CO2
That's right.
production.
The slopes are different. Okay. So the other thing I wanted to show is what sea levels are doing. Sea levels are showing the same behavior.
Mm.
Here's the CO2, but they started rising again 50 years before there was any CO2 production.
80 before there was anything significant.
Yeah. So the climate is changing. We may be contributing to that change in climate, but we're not causing that change.
But if we cut it off, we couldn't expect it just to turn around because we cut it off.
Well, I don't think so. We could drop our consumption back to what it was in the 1900s, but look how much it rose,
Yeah.
right?
So it's not.
So there's another part of the CO2 story which is important, which is that it's known that CO2 production stimulates tree growth.
Yeah.
So there is a feedback between enhanced CO2 and what biological organisms are doing. Did you know that the CO2 that we now have is about 1,000 times less than it was because of animal life, because of plant life?
Yeah.
So the plant life is controlling, to a very large degree, the relationship between the CO2 in the air and the CO2 that's locked in the crust of the Earth.
So it damps it out.
Right.
And
So
what
if you
is-
build a model that says CO2 is increasing, and it's going to continue to increase, and that's what's affecting the climate, and you don't include the delayed growth of plants, which now absorb CO2, then you've built a model which is not correct.
Yeah. So
So
it's both
none of the
trees-
bio connection to what's going on in the CO2 cycle is included in these models, which have been used by the IPCC to argue this doomsday prediction for what CO2.
So it's not just the trees, but this immense area of water with all the plant life in it too.
And you're right. The ocean dissolves CO2 and what's dissolved in the ocean. Some of that, I think, is included in the models, but I can't say much more about that. All right, so this is just a curve that shows all of these things on top of one another. I now want to, and here's the actual measured CO2, which is important. So between about 1900 to the present, there has been a 30% increase in CO2, which you should compare to the 50% increase that I showed you between the warm interglacials and the ice ages. Right?
Wow.
So this, it's clear that CO2 may be related to climate change, but it's not the cause.
Do you think this might be able to slow down the next ice age?
Now, that's a good point. The only thing that we can be certain of is that the interglacial lasts for maybe 20,000 years. How many more years do we have to go before we have to face a decrease in the solar radiation because of the orbital effects? Maybe we should be burning more CO2. I didn't say that.
No,
It's not on the record.
oh, that would be impolitic.
I So the next question that I wanted to ask for you is, do solar changes describe the temperature record? Okay, well, so here's essentially the CO2 record represented by our energy consumption. This red curve is a reconstruction of the, we don't actually have, remember our measure of that 11-year cycle in the brightness of the sun only goes back 20 years. We didn't have satellites that could measure it. But Hoyt and Shatton, looked at the sun and they took the number of sunspots and they built a model where they thought they could actually estimate how bright the sun was just by knowing about sunspots. And their model tells them that the brightness of the sun probably fluctuated back to the 1880s in this red curve. So that's the red curve for the solar contribution. And then they picked out the Arctic air temperature. They're kind of guilty of what we were doing with the Republican records again, right? The Arctic air, I don't know why they picked the Arctic air temperature, but it matches pretty darn well what the solar brightness was doing over that period of time. It certainly matches better the temperature record, which is going up and down in the Earth, than the CO2 does. So the last thing I wanted to say was that it's pretty clear that if you look at the sunspot record as a measure of what the sun is doing, we can see the effect of the sun in rough terms in our historical record. Here's how that works. Okay? This is the sunspot record that goes all the way back to Galileo. So Galileo was the first Westerner to use a telescope to see sunspots and then count them. And ever since they were seen with him pointing the telescope at the sun, we've been counting them. And there was a long period of time when, try as they could, we couldn't see any sunspots on the sun. It was black. Well, it was bright, but no black. That was called the period of the Maunder minimum. And then this rhythm of sunspots is not a rhythm which is very regular. It's sometimes strong and it's sometimes weak, as you can see. The biggest peak was back in 1957.
But the timing is pretty...
Timing is, the cycles fluctuates a little bit between sort of 9 or 12 years between peaks. So when do you think the sun is brighter if we looked at this record? We've already decided, right? When there are more sunspots, the sun is brighter. So the sun should be brighter here, and fainter here.
Yeah.
Okay. Well, guess what? If you go back to the late 1600s, there was a time, remember those wonderful Dutch paintings of people skating over the canals?
Yeah.
You can't do that anymore. It doesn't happen. They don't freeze. There was a time called the Maunder minimum when the temperature in Europe was demonstrably colder than it has been ever. And that was this time right here, when there weren't any sunspots. In fact, Herschel, who was a famous solar physicist, started to look at the price of wheat adjusted for inflation over 700 years in Europe. I don't know how he did it. Well, the why he did it is pretty interesting. So if you look at the price, I mean, economic indicators can be a good record of well, certainly agricultural supplies, and that's a measure of the climate. So the price of wheat, the bountifulness of wheat depends on the growing season, how warm it is. The price of wheat was high in this Maunder minimum period. It was also high during this period right here when there were very few sunspots.
Huh.
You can almost line up these two peaks in the price of wheat.
Let's normalize it a little bit for
Well,
the
just
next
stretch-
presentation.
Yeah, they're stretched to scale, but that's why I do the arrows for you so you can see.
Cool. Lazy man's normalization.
So there's something else going on, right? Remember I showed you that picture of how the sun's magnetic field reaches out and reaches around the Earth. It's
Right.
kind of like a bottle. It shields us from the effects of cosmic rays. Carbon-14 is a radioisotope. It decays with time, and it's produced by cosmic rays that interact with nitrogen in the atmosphere. They form carbon-14. It's breathed by creatures, And when they die, they leave a record of when they last breathed, when they took their last breath. From that, if the production of carbon-14 is constant, we know how old the creature was, or how long ago it died, when the respiration ceased. But also, if we know how old the creature was, we know how much carbon-14 was produced. The carbon-14 is produced by cosmic rays which are shielded by the sun's magnetic field. So what the sun is doing is reflected in the amount of carbon-14 in the Earth's atmosphere. And in fact, the Maunder minimum shows up as a peak in carbon-14. And here's the other minimum, and there's a time back here where there was a dip. That dip corresponds to a time when, according to this record, it must have been warmer. Well, we don't have sunspot records from then. We don't have sunspot records, but the Chinese do. The Chinese recorded sunspots all the way back to 1,000 years ago.
Do you have pinhole cameras or something?
No. The dust and haze from the Gobi Desert, as the sun was setting, provided a nice filter so that you could look at the sun. And those sunspots that we saw in that picture, you could see by eye, if you were looking back 3 Halloweens ago, and you had a neutral density field, you'd see a dark spot in the sun. So the Chinese by eye recorded sunspots, and Jack Eddy, about 15 years ago, went back to the Chinese record, and guess what? In this period of time, the Chinese recorded lots and lots of sunspots. Sunspots means a hotter sun.
And it lasted for a long time, too.
Yeah. Good. We believe that is what we call the medieval warm period. And in fact, if you look at a temperature record, you find out that strange things were happening at that period of time. So in the Southwest, that hotter period of time corresponded to when the Hohokam and the Anasazi and the Mogollon, those Indians disappeared. And by every record I'm able to find, they disappeared because the climate in the Southwest got too warm.
But the crops they couldn't grow crops anymore.
Water, lack of water, just drought conditions. Yeah.
I just see a drought.
Drought, it's drought. But also at that time, remember, also at that time, the eastern coast of Greenland was warm enough to support settlements of 10,000 people from what is now Denmark, the Vikings. The Vikings were colonizing the eastern coast of Greenland at that, growing crops, right? Which in fact died away and vanished as we slid into the period of the Little Ice Age, as the Earth got colder, or certainly as the northern hemisphere got colder. So that warm period was bad news for the Southwest, and it was good news and allowed the settlement of Greenland and the Viking colonies. So there's circumstantial evidence that these temperature variations that we can trace to what the sun was doing to the Earth's system were the root cause of civilizations coming and going. Well, remember what we said about the temperature record in the last 10,000 years.
Yeah.
All of civilization, Western civilization that we know about in the last 10,000 years, may also be, therefore, that consequence of the stability of the climate with these little blips on top of it. I've gone on way too long. Let me just summarize. This is an argument I give to our funding agencies. Within our lifetime, the probability of a major solar storm or brightness change affecting commerce with multi-billion-dollar impact is 90%. It's already happened. 3 years ago, that storm knocked out 2 satellites. There's $1 billion right there.
They actually ceased functioning?
Yeah.
Japanese,
They were lost. Japanese satellite.
and they fried them.
You can design interlocks at such a level, but then if you can't predict the storm, if you don't know it's coming, or if your predictions, even if you do see that it's coming, are not sufficient, then you lose the set, and you sort of ratchet up. There was a Swedish power grid that was also knocked out, suffered damage, even though you'd think by now we would have learned how to protect power grids. This was big enough that in Sweden they hadn't, and that was, I don't know what the damage there was. Within the next 1,000 years, the probability of a major climate change affecting agricultural, global commerce, or civilization's fabric is also likely. It's It's already happened. I think there are examples of how the climate has affected culture and civilization if you go back the last 1,000 years.
So we're gonna get our observatory?
This is not about that. So, my conclusions. Computer models of the Earth's climate do not account for the known climate variability. So the IPCC was an unholy mix of science and politics. It was led by two scientists who had a clear history of arguing for the importance of CO2 and for the importance of ozone effects. And they led that charge. There was a panel of 30, but in the end it came down to them. Many of us in the solar physics community, I was one of them, petitioned the panel to include a fair assessment of the uncertainties in the assumptions of their models and of the astrophysical effects due to the sun. Those arguments do not appear in the IPCC report. They were noted. It was an example of where you take politics and science and you mix them. And it was, we got what we expected. We got politics out of it. Final conclusion is that the solar influences, there is circumstantial evidence and a description of a causal mechanism that makes it clear, to me anyway, that we have to include those effects in understanding or predicting climate change. Thank you.
I'm wondering if particles from the sun would also be collectible on the moon and undisturbed, and one could look at them when it gets there to do this
It's a very good idea.
The moon to assess the solar history.
There is a renewed interest in going back to the moon that our president has described, and there is at least one experiment which actually I was a part of that we thought about trying to actually do that with the SOAST group at the Manoa campus. We thought of a way of actually trying to disentangle the irradiation history of the sun from the undisturbed lunar surface. And the problem that we have is that we don't know how to date. We don't know how to, we can measure the impregnation of material, but without being able to bring things back, it seems very hard.
That's almost necessary to have a lab.
This is not a return mission. It's only to go out there and you may be able to measure something, but how do you know the data?
Well, you have a lunar base, of course, and a full-fledged laboratory there.
I think that there's a possibility you can make a good sense from the lunar record, but nobody knows how to do that. Yeah.
So you showed one a key chart demonstrating that the beginning of the climate change, the recent climate change, predated the carbon emission argument.
Right.
That chart showed a stark rise in the curve.
Yep.
After the World War II.
Yeah, there it is. Now, is there been anything like that that we know of historically?
The sharp rise?
That thing
That
going
sharp-
straight up there.
This thing right here in
No,
CO2.
not that one. That's carbon emission. That one.
This one, the glacier, this is glacier shortenings. So this is a curve of glacier shortenings, and I think you wanted to see the temperature record here.
Okay.
So this temperature record. In fact, this is a tiny temperature change
Fine.
compared to the record that we get from the ice cores. We worry about that temperature change, but the ice core temperature records, and let me show you what I mean.
6 degrees.
So remember what that change was. That was a few tenths of a degree change. The rapid changes in temperature here are about 10 times larger. And we think that some of these changes in temperature, this was the last interglacial period. So here's our interglacial, our warm period. Here's the ice age. Here's the last interglacial. It's roughly 20,000 years. That temperature fluctuated a lot. The temperature fluctuations that we're seeing in that interglacial are about 10 times larger, we think, than the temperature change you referred to in that first graph. So the answer to your question is yes. There are much larger temperature fluctuations that occur naturally than the one that has been attributed to CO2. So be afraid.
What was the most recent one?
There was none. We have, in the last interglacial, it's a pretty clean record of
Let me
temperature.
read past the question. How long has it been since we've had anything like what's going on now?
It would be during the last ice ages.
Which is what time?
That was about 15,000 years ago.
So we haven't had anything like what's going on now for 15,000 years.
As far as we know,
Okay.
but we only have a clear temperature record, right? Remember, I made the point that we measured the temperature record only since 1860.
On the basis of what we do know, we do not know of anything that has gone on in the past that's like what's gone on now.
That's correct. That's right.
So for that period of time, which is not an insignificant period of time, the sun's been very nice to us, but now the sun has decided not to be nice to us?
No, I wouldn't put it that way.
Okay.
I would say that in that curve that shows what the sun is doing,
Nice collect.
Sure, since these chairs are only 1 hour chairs.
I'm sorry. You should come to one of my classes. So, in the solar record, these are the largest fluctuations in solar activity that we know. I am not ready to say that the large temperature record that we see now is due just to the sun. Please don't misinterpret what I'm saying.
It's not due to the sun.
I don't think that all of the temperature change is due to the sun. That's correct.
Not all of it.
I think if we go back and look, so here's solar activity. Here's the northern hemisphere temperature, and it sort of fits that. It goes up and then it goes down for this period of time. That's what intrigues me, right? Remember, the temperature record as it was measured from the British using their canvas buckets. It rose between 1900 and 1940, and then it fell to about 1970. That's this record right here. That's why I think, at least until 1970, the sun was a big part of what was changing the climate. Now, what the climate modelers claim is that the CO2 is the dominant part of the last 30 years. And maybe it is. But it certainly is true that the climate trend, this growing northern hemisphere temperature change that started long before we had the CO2. The CO2 is not the cause of that. It's part of it, probably.
What do you think the cause of it is?
Problem here in climate change, which we should be very worried about, which is we don't understand the problem of climate variability.
How about cows?
More important.
Cows are methane, and methane is a bigger part of
Now, has someone done the population of cows versus
Yes, there are studies of that.
But it isn't just cows, there's lots of other animals that emit methane.
In my mind,
There's
we should be
bioplankton.
investing in understanding what's causing